Algebra 1, Section 10.1, quadratic functions. We'll start out with quite a bit of vocabulary. Let me just say that what I could do, and I could make these notes really long, is I could put out a definition for each one of these things. And again, my video would be longer, my notes would be long. I've decided instead to just put out the important words and then we'll talk about each one of them briefly. I would highly encourage each of you to also read section 10.1. And I think you should always read the section, but especially now, especially as we kick off this chapter, which has got a lot of vocabulary, make sure you read through 10.1, look at the bolded highlighted terms and the examples themselves before you attempt the 10.1 homework. Quadratic function. Function has taken on a little bit of a different definition at different times in the year. I think the book doesn't do a great job of having a specific definition for function, but here it's very simple to understand. An equation would be something that has a single variable that we can solve, whereas a function is something that's got two variables which we could graph. Okay, and we're going to deal with both of those, and we'll deal with how those things do link up. But for example, a quadratic function let me say it this way. Standard form, which we did touch on in chapter 9, is in the form ax squared plus bx plus c. Okay, and if it were a cubic, well, then it would be ax to the third plus bx squared plus cx plus d, etc. Okay, but for quadratics, this is what it would look like. The key point is that it's in descending order. The quadratic term is first, the linear term is next. That means x to the first. The constant is last. Constant would be an x to the 0. And an equation that we could solve would be something like this, and maybe it's equals 0, right? And we will learn in this chapter how to solve quadratic equations of that variety, okay? Now, the function that they're referring to, though, is like this. Y equals, okay, something we can graph. It has an input and an output, an x and a y. This is a quadratic function, and this is also considered standard form, okay? Now, moving on, a quadratic parent function. We did discuss what a parent function is, and that's simply the simplest form of whatever family of functions you're dealing with. So if it's a line, y equals x was the parent function. If it's an absolute value function, it's y equals the absolute value of x. Well, the parent function then would simply be y equals x squared. Okay. Now, with that, as we do know what the graph would look like for these, the graph of the parent function would have would pass through the origin and have symmetry about the y-axis. We'll talk about that symmetry here in just a second. The shape of this graph is what's known as a parabola. We did encounter this at least once before, where we were graphing lines, quadratics, these, and absolute value functions. Well, now we're going to get really specific in chapter 10 for the quadratics. And the name of this graph that produces this U-type function, all the quadratics produce this kind of graph, is parabola. So that shape, this shape, is known as a parabola. Okay. Now, the parent function would look like this, and we could get specific values along the graph there using a t-chart. They don't have to look like that, right? They can appear in different locations. They can be wider or narrower. They can open up or open down. I think of this one as opening up, right? Like you could pour something into it, a liquid, like a cup. Whereas if it was opening down, it's kind of like you put it on a shelf to dry and the water to drip off. That would be opening down. So I think of this type as opening up. Another example would be something like this, where it appears in a different location. This one's a little bit narrower and it opens down. Okay, so both of those are parabolas. Now, axis of symmetry. There is a line that you can draw that would be kind of the mirror line for the graph. So like this, right? Whereas every point on this side of the graph could be reflected over that line to produce a point that's on this side of the graph. Or you could, another way to say it is you could flip that over this line and the parabola would look exactly the same. Well, for this one, for the parent function, and for any that have a vertex, oh, that was the next word, vertex. Any of them that have a vertex that's on the y-axis, the y-axis is that axis of symmetry. It has an equation of x equals 0. This one, it's not. Let me try that again. It's not the axis of symmetry, it's not the y-axis, but it still has an axis of symmetry, meaning that all of the points on one side could be reflected over that line to land on the other side, specifically on that parabola. That's called the axis of symmetry. Okay, and then finally, vertex, I just used that word, would be the point where the axis of symmetry does intersect with the graph itself. Okay, so I've just circled it on the two examples we've used. And specifically, they're either a minimum or a maximum. Okay, so on the first graph, that would be a minimum. The minimum actually is that point right there. Okay, because this graph does go up forever in this direction. It goes up forever in this direction. The lowest that it'll ever get is this point right here. So that point is the vertex, and it's the minimum. Specifically, when we talk about minimum, we're talking about the y value of the ordered pair that is the vertex. So this one's at 0, 0. Its minimum is 0. The vertex is the ordered pair. The minimum is the y value. Okay. Conversely, this is a maximum. This is the highest this will ever get. This point right here is a maximum. And maybe the ordered pair is, I don't know, -3, 2. Okay, so the maximum then is the y value of the 2. Now, what does this look like for examples? Well, here's a problem right away that's going to talk about maximum and minimum. Identify the vertex and then tell whether it's a maximum or a minimum. So we can do that. And this point right here is an ordered pair that we can identify as being 1, 2. 1, 2. And you can use the abbreviation if you like to. That's a maximum. MAX for maximum. Okay, the highest it'll ever get is 2. This point is a minimum, and it's at the point 2, -4. MIN for minimum. Okay? What else? Make a table of values and graph the quadratic function y equals 1/3 x squared. I have a graph here. Y equals 1/3 x squared. Now, I think there are 12 graphs on the homework assignment, so do please download and print the graph paper that I have put at multiple places on my website. There's 6 graphs per page, so you'll probably have to print 2 pages of that just to do this one assignment. Please use my graph paper and do an accurate job. Okay, so we'll use a t-chart here. Now, we will have other methods moving forward for graphing parabolas, but you'll always have the use of a t-chart. You can always fall back on that. And I like to start with 0. Okay, so 0 is an input. And think about that. 0 squared is 0. 0 times 1/3 is 0. So input 0, output 0. There's a point right here at the origin. Okay. Think about this now. Do you want to plug in a 1? 1 squared is 1 times 1/3. I'd have an input of 1, an output of 1/3. Is that what we want to do? It wouldn't be the worst thing, and I'm not telling you not to, but I can think of better numbers than 1. If you want to make things easier on yourself, how about 3? 3 squared is 9. 9 times 1/3 is 3. Input 3, output 3. That's an easier point to graph. If I can, and sometimes it's not possible, but if I can, I like to find ordered pairs where both numbers are where a grid line, where the numbers meet where two grid lines on the graph paper will cross. Okay, so 3, 3 to me is better than 1, 1/3. By the way, if 3 gives you a 3 as an output, so will -3. On this simple example, will give you 3. Because -3, all of it squared, as in -3 in parentheses, squared would be +9. 9 times 1/3 is 3. So we also have a point at -3, 3. Okay? Now, do you want to pick 4? 4 squared is 16. Times 1/3 would be 16/3. I don't like that. 5 would not be convenient. 6 is good, though. 6 squared is 36. 1/3 of that would be 12. Similarly to the 3's, -6 squared is 36 times 1/3 is 12. Now here and also on the graph paper, that's a little bit off the graph, but I'll still include it. It's right there. And -6, 12 is right here. Okay. It's good to have more than 3 points if you can. Okay. Now, a word about graphing these parabolas. I'm not looking for perfection. I'm not an art teacher, but try to have something that shows a curve. Okay, it's not a dot to dot. Don't draw a line segment from here to here and then a different line segment from here to here. That's not what it's doing. It's a continuous kind of a gradual curve. So show that. And it's also not an absolute value graph, right? Stop and think about what those look like. If the vertex were here and it passed through this point and it just kept going, the graph would go this way, okay? Well, this is not that. This is a curve, so show it as a curve that passes through your points. And again, 5 points is a good a good goal to aim at. But if you want to get 7 or 9, sometimes that's necessary. Minimum 3, probably 5. If you can get 7 or more, that's even better. Just kind of depends on the problem. All right, back to a few more examples. Here's their graph. Notice the symmetry. It's symmetrical over the y-axis. Again, that axis of symmetry that is the y-axis, it has an equation that is x equals 0. If it were over 2 units, it'd be x equals 2. If it were to the left 4 units, it'd be x equals 4. Vertical lines are always of the form x equals a number. That'll be important one someday soon. But anyway, I was pointing out the symmetry. Here's the point. Well, I'm not crazy about their choice of 2, but 3, 3, and then here's negative 3, 3. Both of them are the same distance from the axis of symmetry. This problem says use the graphs and then to list them from widest to narrowest. Make sure that you read the directions carefully on a problem like this. You don't get them backwards. Widest to narrowest. Okay, so here's the deal with these. This has everything to do with the first number. This number 1/2, this number negative 3, this number would be assumed to be negative 1, right? Negative x squared is like saying negative 1 times x squared. Now, for as far as telling whether they're widest or whether wider or narrower, it really doesn't matter whether you consider the negative or not, okay? What the negative does, I'll tell you quickly, is controls whether the parabola opens up or down. You'll see that because they did this on calculator windows. You'll see that in a second. So a negative lead coefficient, a negative a value, is going to open down. A positive number is going to open up. And you'll get experience with this as you graph these in the homework on 10.1 and throughout as well. Okay, so I'm just going to look at 1 and 3 and 1/2, kind of regardless of whether it's negative or not, as I determine whether it's widest or narrowest. And stop and think about that. When you take a number and then square it, and then you multiply it by 1/2, what happens? Or you multiply it by 3, what happens? Well, when you multiply it by 1/2, it gets cut down, whereas when you multiply it by 3, it gets accelerated up, if you will, okay? It gets stretched. So the narrowest one is actually going to be the 3, the widest one is going to be the 1/2, and the one that's in the middle will be 1. I'll show you that with their calculator windows too. Here's what these 3 functions look like in the order they gave them to us on calculator windows. The narrowest one is the one that has the 3 here because it's causing it to grow faster. The widest one is the one that has the 1/2, and then again in the middle is the one that has the 1. Okay, and again notice 1/2 is positive. There's the parabola that's opening up, whereas these two are opening down because their lead coefficient was negative. And there they have them listed in order. Okay, I think we have 2 more examples. One says graph the quadratic functions y equals 3x squared and then also y equals 3x squared minus 2. I'll leave that one. I'll actually just scroll to their answer, trying to keep this video reasonable in length. And here's a t-chart that they use for both of them. They picked a kind of a standard 5 set of numbers here, 2, 1, 0, negative 1, 2. Here's your outputs for y equals 3x squared. Here are your outputs for y equals 3x squared minus 2. And as they graph them, they did them in different colors. You'll notice that y equals 3x squared minus 2 is the same exact size and shape, but it's shifted down 2. Well, that's not a coincidence that this number here is negative 2. That's what happens when you plug in values for x, square it, multiply it by 3, but then subtract 2 from them. Everything's going to be 2 down, okay? So just so you understand, the red graph is y equals 3x squared. The blue graph is y equals 3x squared minus 2. Now, if you get asked this in the homework, feel free to put them on the same set of axes. All right, now one other thing. is the gravity problem. H equals negative 16t squared plus c is in standard form. And as I say that, you might look at that and say, that doesn't really look like standard form. Standard form is y equals ax squared plus bx plus c. Well, let me explain. First of all, x and y versus t and h. Who cares what letters they use? Okay, so in h equals negative 16t squared plus c, c is going to be a number, okay, but the variables are t and h. T is for time, h is for height, but they function just as x and y would, okay? So t is the input, h is the output. T stands for time, h stands for height, and this is the gravity problem. You drop something, and then you track its height over time. That's what this is functioning as. Now, the a value is the negative 16. This has to do with gravity. Think about it, you throw something up in the air. Throw something up in the air, eventually it reaches a peak and it comes back down. Why is that? Well, because gravity is stronger than your initial velocity. And you throw something up in the air at a certain speed, gravity eventually takes over as time goes on. That's what's going to happen in this quadratic term. The time is going to get squared. Think about like 1 squared is 1, but then 2 squared is 4. And then 3 squared is 9. As time goes on, that number is getting huge, and it's going to multiply the negative 16. It's negative because it's pulling down, and that's going to eventually take over whatever your initial velocity was. Okay? Now, we're not going to deal with an initial velocity here in the first section of the chapter. It's simply going to be dropped, and therefore there is no middle term. See, the b, this initial velocity that I've been talking about, that would be the b value. It's understood to be 0 here. We're going to see an example in a minute where it just says an orange is dropped, okay? Not like it was tossed up first and then dropped, and certainly not like it was fired up in the air, 80 feet before before gravity took over. It's just simply dropped. So gravity immediately starts pulling down. It immediately starts going down. And then the c value is just the initial height. So c is really just the same for both of these. The c value is the initial height. Okay, so with that, I give you the example where it says a monkey drops an orange from a branch of 26 feet above the ground. The force of gravity causes the orange to fall toward Earth. The function h equals negative 16t squared plus 26 gives the height of the orange h in feet after t seconds. They want us to graph this quadratic function. Now again, just to keep this video reasonable in length, I'll just show you what their graph looks like. But let me first say again, negative 16t squared, that's what we saw in the previous example. That's gravity in terms of feet per second squared, okay? Don't worry about the units right now, but it's gravity. If it were in meters, it would be a different number. It would still be negative. If I remember right, it's 4.9, negative 4.9. So anyway, this is in feet. The 26 is just the initial height. You saw that in the problem, okay? So as we plug in, and you absolutely could do a teach right here, plug in 0 and 1 and 2. They did that. We get these numbers. At 0 seconds, we're still at 26 feet. This is when the monkey is just about to drop the orange. At 1 second, we would plug 1 in, and the output is 10. Check that if you like. The output is 10. Meaning that it's dropped from 26 to 10. If you plug in 2, we're going to be at negative 38. Okay? Now that's going to produce this graph right here, such that 2, negative 38 would be like down here. Okay? Now, do we care to know about 2, negative 38? Well, no, because the orange has hit the ground sometime between 1 and 1.5 seconds. Okay? We could solve for that if we would plug 0 in for h. We will do that one day as well to solve an equation in chapter 10 that is 0 equals negative 16t squared plus 26. Not today, but sometime soon. So anyway, the portion of the graph that's relevant to us is what they have in red. The full parabola would look something more like this, with arrows continuing in that direction. But what they show in red is relevant to the monkey dropping the orange problem. Started up here at 26, dropped, here's where it is at 110. They missed a little bit, didn't they? It should be down just slightly. Anyway, and then it hits the ground here, and that's it, right? It's not going to continue to go underground. Therefore, we stayed in the first quadrant. You're not going to have negative time. You're not going to have negative height for the orange dropping problem, okay? Now, again, please use my graph paper as you do graphs like this, even if it's just relegated to the first quadrant, do that, and you just will not use the second, third, and fourth quadrants. All right, thanks for tuning in. Good luck.